Usually we'll tell alkali metals are having more electropositive nature, but lithium is having low electropositive nature. One speciality here, lithium combines with nitrogen to form nitrate, but other alkali metals will not combine with nitrogen. All the carbonates and bicarbonates are soluble in water, and their solubilities are increased rapidly on decreasing the group. The washing soda or sodium carbonate will be manufactured by the advantage of low solubility of sodium hydrogen carbonate. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today we are starting up session 2 from the chapter S block elements. In the last session, we have discussed about general introduction of S block elements. In that, group 1 elements that will be also called as alkali metals, physical properties and chemical properties of those alkali metals we have discussed in the previous session. In today's session, anomalous properties of lithium, diagonal relationship, general characteristics of the compounds of the alkali metals. These are the contents which we will discuss in this session. First we will see anomalous properties of lithium. While I was telling about, or I was giving the introduction about the alkali metals, in that time only I have told some of the anomalous properties are present in this block according to some of the elements. Okay, anomalous means what? One element which is not giving the similar properties like other elements, that will be considered as anomalous properties. Like that, lithium is the one element in the group 1 which will not give the similarities of other elements in the most of the times. Lithium, the first element of the alkali metals, differs from the rest of the group in many respects. This anomalous behavior of lithium is due to the following reasons. Why it will be having anomalous properties? What were the reasons behind this? Small size of lithium atom and its ion. Lithium is having very small size because it's the first element. So it is having very small size. Higher polarization power of lithium plus, resulting is increased covalent character of its compounds, which is responsible for their solubility in organic solvents. Higher polarization power of lithium plus. This is the cation. It is having high polarization power. That is also one reason. Comparatively high ionization enthalpy and low electropositive character of lithium as compared to the other alkali metals. It is having high ionization energy and low electropositive elements. Usually we will tell alkali metals are having more electropositive nature, but lithium is having low electropositive nature. It is the one of the reason. Non-availability of d orbitals in valence shell. Here d orbital only is not present in the overall shell of the lithium. Strong intermetallic bonding. It is having intermetallic bonding having much strength. Next, difference between lithium and other alkali metal. What are the differences are present between lithium and alkali metals? Some of the properties in which lithium differs from other members of its group, illustrating its anomalous behavior, are as follows. Lithium is harder than sodium and potassium, which are so soft that can be cut by a knife. Lithium is very hard, but sodium and potassium are soft metals. We know that we can cut by those from knife itself. The melting point and boiling point of lithium are comparatively very high. Since it is very hard metal, it is having melting point and boiling point very high. Lithium forms only monoxide with oxygen, and other alkali metals also form peroxide and superoxides. Lithium will form only monoxide with oxygen, but other alkali metals will form superoxides, also peroxides. Lithium combines with nitrogen to form nitrates, while other alkali metals do not. One speciality here, lithium combines with nitrogen to form nitrate, but other alkali metals will not combine with nitrogen. Lithium chloride is deliquescent and crystallizes as a hydrate, lithium chloride hydrate, whereas other alkali metal chlorides do not form hydrates. Lithium chloride will form hydrated forms or hydrates, but other alkali metal chlorides will not form a hydrated molecules. These are the differences between the lithium as well as alkali metals. Next, we'll see diagonal relationship between the elements in the periodic table. Diagonal relationship, you know that one of the element which is diagonally present another element shows the similarity in the periodic table. A relationship with the periodic table by which certain elements in the second period have a close chemical similarity to their diagonal neighbors in the next group of the third period is called diagonal relationship. Whichever it is present in the second group, second period, it will be chemically similar to the third group in the third period. Okay. Following reasons: similarity in the ionic sizes, similarity in polarizing power or charge. Ionic sizes will be having same or similar, similarity in polarizing power also. Next, similarities between lithium and magnesium due to diagonal relationship. Usually lithium and magnesium are diagonally placed in the periodic table. So, what are the similarities between those elements? Both form chlorides and bromides that hydrolyze slowly and are soluble in ethanol or alcohol. Okay. Both lithium and magnesium will form chlorides and bromides and will be soluble in ethanol. Both form colorless or slightly colored crystalline nitrides by direct reaction with nitrogen at high temperature. Both will form colorless or slightly colored crystalline nitrides by direct reaction with nitrogen at very high temperature. Both burn in air to give normal oxide only. Both will react with air or burn with air, so to form oxides. Both form carbonates that decomposes on heating. Oxides of lithium and magnesium do not combine with excess of oxygen to form any superoxide. It will form oxide, but with excess of oxygen these will not react to form superoxides. Both lithium and magnesium are harder and lighter than other elements in the respective groups. Both are having harder also, both are having lighter groups also with respect to the other groups. These are the diagonal relationship points with respect to lithium and magnesium and the similarities between those two elements. This is how the diagonal relationship will be applicable in the periodic table. Next, general characteristics of the compounds of the alkali metals. What are the general characteristics of compounds present in the alkali metals? We will see one by one, that is oxides and hydroxides. All alkali metals when burnt in air form different kinds of oxides. For example, the alkali metal on reaction with limited quantity of oxygen form normal oxides of formula M2O. This is any alkali metal which reacts with oxygen, it will form metal oxide. M can be lithium, sodium, potassium, rubidium or cesium. When heated with excess of air, lithium forms normal oxide, sodium forms peroxide. We have discussed that lithium will not form any superoxide, so it will form only normal oxide, but sodium will form peroxide, whereas potassium, rubidium and cesium form superoxides having general formula MO2. Except lithium, other will form, some of them will form peroxide, some of them will form superoxides. The alkali metals, their oxides, peroxides and superoxides readily dissolve in water to produce corresponding hydroxides which are strong alkalis. Whatever oxides, superoxides or hydroxide will form from the metals, it will dissolve in water to form hydroxide and those will become strong alkalis or strong bases. See here, sodium plus water, sodium hydroxide with the liberation of hydrogen water. This is sodium oxide, this is sodium hydroxide, this is sodium peroxide, it will also form sodium hydroxide. This is potassium oxide, potassium hydroxide. Thus, peroxide and superoxide also act as an oxidizing agent since they react with water forming H2O2 and O2 respectively. The hydroxides of all alkali metals are white crystalline solids. They are strongest of all bases and readily dissolve in water with the evolution of much heat. It will act as strong oxidizing agent also, and hydroxides of all alkali metals will be white crystalline in nature and these are the strong bases which will dissolve in water with the evolution of much heat, which will form exothermic reactions. Next, halides of alkali metals. When we'll tell halides, when metal will react with halogens, it will form halides. The alkali metals combine directly with halogens under specific conditions, forming halides of general formula Mx. These halides can also be prepared by the action of aqueous halogen acids on metals oxides, hydroxide or carbonates. Metal oxide plus hydrogen halide will form metal halide with the liberation of water. This is metal hydroxide plus halogen halide. This will also form metal halide with water. This is metal carbonate plus hydrogen halide. It will form metal halide plus carbon dioxide plus water. M is nothing but lithium, sodium, potassium, rubidium or cesium. X is nothing but halogen. It may be fluorine, chlorine, bromine or iodine. All these halides are colorless, high melting crystalline solids having high negative enthalpies of formation. Okay, this is how from the carbonates, from the metal oxides, from the hydroxides, halides will form. The solubility of the most of the alkali metal halides except those of fluorides decreases on descending the group, since the decrease in hydration energy is more than the corresponding decrease in the lattice energy. Decreases down the group because hydration power will be decreases. Due to small size and high electronegativity, lithium halides except lithium fluoride are predominantly covalent and hence are soluble in covalent solvents such as alcohol, acetone and ethyl acetate. Due to small size and high electronegativity, lithium halides except lithium fluoride are predominantly covalent. Except lithium fluoride, all our lithium halides are predominantly covalent and soluble in covalent solvents only. Okay, covalent solvents are nothing but alcohol, acetone and ethyl acetate. In contrast, NaCl, that is sodium chloride, being ionic, it is insoluble in organic solvents. Sodium chloride, which is insoluble in organic solvent, but except lithium fluoride, all lithium halides will soluble in organic solvents only. Due to high hydration energy of lithium plus ion, lithium halides are soluble in water except lithium fluoride, which is sparingly soluble due to its high lattice energy. Due to high hydration energy of lithium plus ion, lithium halides are soluble in water except lithium fluoride, which is sparingly soluble due to its high lattice energy. For the same alkali metal, the melting point decreases in the order. How? The alkali metals, the melting point will decrease. First fluoride, next chloride, next bromide, next iodide. Okay. For same alkali metal ion, the lattice energies decreases as the size of the halide ion increases. As the size of the halide ion increases, the lattice energy will decrease. For the same halide ion, the melting point of lithium halides are lower than those of the corresponding sodium halides, and thereafter they decreases as we move down the group from sodium to cesium. The low melting point of lithium chloride as compared to sodium chloride is probably because lithium chloride is covalent in nature and sodium chloride is ionic in nature. Because of sodium chloride is ionic in nature and lithium chloride is covalent in nature, the melting point of lithium halides are lower than that of corresponding other sodium halides. Next, salts of oxo acids. An oxo acid is an acid that contains an oxygen atom bounded to a hydrogen atom and at least one another element. Example, sulfuric acid, phosphoric acid and nitric acid are all oxo acids. Since the alkali metals are highly electropositive in nature, their hydroxides are very strong bases and hence they form salts with all oxo acids. They are generally soluble in water and stable towards heat. This sulfuric acid, phosphoric acid and nitric acid all are oxo acids because whatever the in between it is forming the alkali metal, they are highly electropositive in nature and it will form whatever the hydroxides are forming from that, they are very high strong bases, and those salts which will form by this, it will soluble in water and resistant to heat. Next, decomposition of metal carbonates. The carbonates of alkali metals are remarkably stable up to 1273 Kelvin above, which they first melt and they eventually decomposes to form oxides, that is lithium carbonate. However, is considerably less stable and decomposes readily. Okay, this lithium carbonate will resist heat 1273 Kelvin. It will form lithium oxide plus carbon dioxide. This is presumably due to large size difference between the lithium and carbonate, which makes the crystal lattice unstable because the size difference between their carbonate and lithium. Being strongly basic, alkali metals also form solid bicarbonates. No other metals form solid bicarbonates, though ammonium hydrogen carbonate also exists as a solid. Lithium, however, does not form solid bicarbonate, though it does not exist in solution. These are the two exceptions. No other metals will form sodium bicarbonates, and lithium, however, does not form solid bicarbonate. These are the decomposition of metal carbonates you should know. And all the bicarbonates on gentle heating undergo decomposition to form carbonates with the evolution of carbon dioxide. What all bicarbonates will be gentle heating undergoes, it will form carbonates with the evolution of carbon dioxide. All the carbonates and bicarbonates are soluble in water and their solubilities increase rapidly on descending the group. All the carbonates and bicarbonates are soluble in water and their solubilities are increased rapidly on decreasing the group. Solubility will increase. This is due to the reason that lattice energies decreases more rapidly than that of hydration energies on moving down the group. These are the reasons you have to understand before going to the trends which are following in the group. Next, preparation and properties of some of the compounds. Which are the main compounds will be used in laboratories, how it will be prepared or how it will be manufactured, and what are the methods to manufacture and what are the uses of those compounds in usually laboratory techniques. So, we should understand. First one, sodium carbonate, that will be called it as washing soda. See here, Na2CO3 decahydrate. Sodium carbonate is an industrially important compound. It is manufactured by Solvay's process. Usually, sodium carbonate will be used in many industries. So, it will be prepared or manufactured by Solvay process. In this process, advantage is taken of the low solubility of sodium hydrogen carbonate, whereby it gets precipitated in the reaction of sodium chloride with ammonium hydrogen carbonate. The raw materials for the manufacture of sodium carbonate are brine, ammonia, carbon dioxide and calcium hydroxide, which are obtained from the limestone. By the Solvay process, the washing soda or sodium carbonate will be manufactured by the advantage of low solubility of sodium hydrogen carbonate. Manufacture of sodium carbonate by Solvay's process, that will be called as ammonia Solvay process. The ammonia Solvay process consists of the following steps. In the first step, the sodium hydrogen carbonate is prepared by passing CO2, that is carbon dioxide, in a concentrated solution of sodium chloride, that is brine solution. Okay. In the concentrated sodium chloride solution, this CO2 or carbon dioxide will be passed saturated with ammonia. That should be saturated with ammonia. During this reaction, ammonium carbonate followed by ammonium hydrogen carbonate is formed, shown in the following chemical reactions. This is ammonia saturated with water, carbon dioxide will be passed, ammonium carbonate will be formed. In the ammonium carbonate, again water and carbon dioxide will be treated, ammonium hydrogen carbonate will be formed. In ammonium hydrogen carbonate, when we treated with brine solution, that is sodium chloride solution, ammonium chloride and sodium bicarbonate will be formed. These are the steps which involved in step 1. In step 2, sodium hydrogen carbonate is heated to about 300 degrees Celsius to decompose into sodium carbonate and carbon dioxide. Sodium carbonate is recovered and carbon dioxide is reused. Whatever this sodium hydrogen carbonate we got from step 1, which will be heated or decomposed to form sodium carbonate and carbon dioxide and water. Okay, here sodium carbonate will be formed. In step 3, ammonia can be recovered by treating ammonium chloride with calcium hydroxide, forming calcium chloride and ammonia. The ammonia is reused, but calcium chloride is a waste. Here we got ammonium carbonate that will be treated with ammonium chloride and calcium hydroxide. Here ammonia will form and calcium chloride and water. But here calcium chloride is a complete waste. Note, Solvay process cannot be extended to the manufacture of potassium carbonate because potassium hydrogen carbonate is too soluble to be precipitated by the addition of ammonium hydrogen carbonate to a saturated solution of potassium chloride. This Solvay process, though sodium and potassium is having similar properties, we cannot use this process for potassium, only this has to use for sodium. Why means potassium carbonate or potassium hydrogen carbonate is too low to get precipitate with addition of ammonium hydroxide. That's why only sodium carbonate can be formed by Solvay process, not for potassium carbonate. Next, properties of sodium carbonate. Sodium carbonate is white crystalline compound soluble in water but insoluble in alcohol. This is white crystalline solid and it is soluble in water, not in ethanol. It forms a strongly alkaline aqueous solution. Sodium carbonate decahydrate is commonly called washing soda. Okay. It is readily soluble in water. On heating, the decahydrate loses its water of crystallization to form monohydrate. Above 373 Kelvin, the monohydrate becomes completely anhydrous and changes to a white powder called soda ash. This is sodium carbonate decahydrate. At 375 Kelvin, it will form sodium carbonate monohydrate. That monohydrate less than 373 Kelvin, it will form sodium carbonate. Next, hydrolysis of sodium carbonate. Carbonate part of sodium carbonate gets hydrolyzed by water to form an alkaline solution. It will form alkaline solution. So, next, uses of sodium carbonate in water softening, laundering and cleaning. Washing soda in the detergents and all we will use to wash or to laundering. In the manufacture of glass, soap, borax and caustic soda. In glass manufacturing, in soap or borax and caustic soda will be used. In paper, paints and textile industries also, it is an important laboratory reagent both in qualitative and quantitative analysis also. While you people are doing the salt analysis, this sodium carbonate in the solution form or sometimes in the solid form you people will use. Next, sodium chloride. The main source of sodium chloride is seawater, where usually we will get that NaCl in seawater. Seawater contains 2.7 to 2.9% by mass of the salt. Approximately 50 lakh tons of salt are produced annually in India by solar evaporation. Production of sodium chloride from seawater. NaCl is obtained from seawater by evaporation in the presence of sunlight. Crude sodium chloride contains sodium sulfate, calcium chloride and magnesium chloride as impurities. By the sunlight evaporation, we can dry out this sodium chloride, but that crude sodium chloride will contain sodium sulfate, calcium chloride and magnesium chloride as impurities. To obtain pure sodium chloride, the crude salt is dissolved in the minimum amount of water and filtered to remove insoluble impurities. The solution is then saturated with hydrogen chloride gas. Crystals of pure sodium chloride will separate out. Here hydrogen chloride, that is HCl gas, will be passed to form or to get pure form of sodium chloride. Calcium and magnesium chloride being more soluble than sodium chloride remain in solution. Sodium chloride melts at 1081 Kelvin. Calcium and magnesium chloride is being more soluble than sodium, right? That's why it will be remain in solution. This thing will be separates out. It has a solubility of 36 gram in 100 gram of water at 273 Kelvin, the solubility does not increase appreciably with increase in temperature. Uses of sodium chloride, it is used as a common salt or table salt for domestic purpose. It is used in the preparation of sodium oxide, sodium hydroxide and sodium carbonate. So here it is having the main use for the domestic purpose as well as in the preparation of some of the sodium hydroxide and sodium carbonate also. Next, sodium hydroxide, which will be called as caustic soda, and it is a strong base. We know that. How it will be prepared, we'll see. Caustic soda or sodium hydroxide is one of the most important chemicals of industrial use. Caustic soda must be handled carefully because it is caustic to touch and causes painful burns. Manufacture of sodium hydroxide by Kastner-Kellner's process. How it will be manufactured? Caustic soda is manufactured by Kastner-Kellner's electrolytic process. This process is carried out in an electrolytic cell known as Kastner-Kellner's cell. A brine solution, saturated solution of sodium chloride will be called it as brine solution. It is electrolyzed in using mercury cathode as well as carbon anode. Sodium metal is discharged at the cathode, combines with mercury to form sodium amalgam. See, sodium, it will leave 2 electrons to form, it gets reduced, and here sodium plus mercury forms sodium amalgam. Next, chlorine gas is evolved at the anode. It is get oxidation. The mercury containing dissolved sodium is sent to the another chamber called decomposer, where sodium reacts with water forming sodium hydroxide. After decomposing, it treated with water to form sodium hydroxide and hydrogen. Decomposer is packed with graphite blocks as hydrogen is easily liberated over graphite sulfur. Okay, this sodium amalgam is treated with water. It will form sodium hydroxide, hydrogen gas and mercury. The solution which flows out from decomposer is NaOH solution, which is evaporated to dryness. Next property, sodium hydroxide is deliquescent solid, so it absorbs moisture and carbon dioxide to form liquid carbonates and bicarbonates. Therefore, sodium hydroxide is always stored in airtight bottles. It will react with moisture to form oxides or carbonates or bicarbonates. Uses: sodium hydroxide is mainly used for the following purposes: refining of petroleum, making paper, in the textile industries for mercering cotton fabrics, printing and dyeing, manufacture of soap, mainly this industry, purification of bauxite, refining of oils and fats. These are the uses. Before only we have told sodium hydroxide is having a more uses. Next, sodium bicarbonate, which will be called as baking soda or sodium hydrogen carbonate. Sodium bicarbonate is commonly called as baking soda because it decomposes on heating to generate bubbles of carbon dioxide. So, it is a white odorless crystalline solid, completely soluble in water but slightly soluble in ethanol. It is the mildest of all sodium alkalis. Comparative to all sodium alkalis, it is the very mildest. Preparation: sodium bicarbonate is prepared from purified aqueous sodium carbonate solution by passing carbon dioxide. Sodium carbonate solution, how it will be prepared? When sodium carbonate solution is present, that time carbon dioxide will be formed. See here, sodium carbonate, water and carbon dioxide, sodium hydrogen carbonate will be formed. The bicarbonate precipitates out as it is less soluble, it is separated and dried. Sodium bicarbonate is also made as an intermediate product in the Solvay process. In the Solvay process also we have seen sodium carbonate will be formed. It is an intermediate in that process. Next, uses: baking powders in the cake manufacturing, using in the treating wool and silk, fire extinguishers, mild antiseptic for skin infections, etc. Usually this will be used as in a domestic purpose also, and treating wool and silk, fire extinguishers, also antiseptic medicine. Next, biological importance of sodium and potassium. What are the biological importance are there? Sodium and potassium are essential to all organisms. Their monopositive ions are structure promoters for both polynucleic acids and proteins. For polynucleic acids and proteins, their mono positive ions will be structure promoters. Potassium is an important enzyme activator and plays an important role in nerve action and cardiac action. This potassium will give the impulses. Potassium is required in the cell glucose metabolism and protein synthesis. It has been found that in most animal cells, the concentration of sodium ion is 75 times the concentration of potassium ions. As a typical example, in blood plasma, sodium is present to the extent of 143 millimole per liter, whereas the potassium level is only 5 millimole per liter within the red blood cells. Sodium is relatively harmless except in excessive amounts, whereas potassium is moderately toxic to mammals when injected intravenously, otherwise it is harmless. These are the biological importance of sodium and potassium. In the next session, we'll discuss about group 2 elements, that is alkaline earth metals, its ionization enthalpies, hydration enthalpy, physical and chemical properties. I hope you have understood completely whatever we have discussed today. So we'll meet in the next session. Thank you.